Good evening. We are going to do the second part of our chapter Oscillations. The first part we had discussed in our previous session. So today we start our session with the Four's law for simple harmonic oscillations. Now in our previous session we discussed that the acceleration of a simple harmonic oscillator is given by minus omega square x, where x stands for the instantaneous displacement of the particle from the mean position. For example, suppose this is the mean position x equal to 0. The maximum displacement from the mean position to the right is what we call as the plus a, the amplitude, and to this side also we have minus a, the maximum displacement. At any instant, the displacement of the particle from the mean position is what we denote as x, and for any simple harmonic oscillator, the acceleration is minus omega square x, where omega is the frequency, angular frequency of this oscillation. So you may write from Newton's second law, F is equal to ma, which is m into minus omega square x, and you may write this as F equal to minus m omega square x, where k is equal to m omega square, because the mass of the oscillator and the angular frequency of the oscillator are constants. So you may take this m omega square as a constant, k, and you will see that you may write this as minus kx. Now you will see that this is not unfamiliar to you. We did this as the Hooke's law in our chapter Work, Energy, Power. We had a force which was called the restoring force, the spring force, in our where we had a spring which is connected to a mass n. If you displace it to the right, this being the equilibrium position, if you displace it to the right, we have a spring force pulling it back to the left, to the mean position. If you compress it, then the spring force will bring it back to mean position. So then we discussed about what is called as a spring force, which is a restoring force. And the property of a restoring force is that it is always opposite to the displacement. Not only that, it is directly proportional to the displacement. You pull it to the right, further greater the displacement, greater will be the spring force or the restoring force trying to bring it back to equilibrium position. So this k, which is m omega square in the case of a simple harmonic oscillator, happens to be the spring constant. In our chapter Work, Energy, Power, we have discussed the same thing and we have called this k as the spring constant. So from here you will see that omega is now equal to root of k by m, where k is the spring constant. Now for this, such a simple harmonic oscillator, which is a linear oscillator, the block and the spring system, you will see that the time period is equal to, the time period we know is 2 pi by omega, or you may write this as 2 pi by omega is, this will be by omega, so this will be m by k. So you see the time period is dependent on, see, suppose you have a very stiff spring. For stiff spring, k is larger. Larger k would mean smaller time period, and larger k would mean larger angular frequency. So for stiff springs, you have larger angular frequency and smaller time periods. So this is what we have as Four's law in any simple harmonic oscillator. Next, what we need to discuss is the energy of a simple harmonic oscillator. Any simple harmonic oscillator will have both kinetic energy and potential energy. So the total energy can be taken to be the sum of kinetic energy plus the potential energy. Now potential energy, because work is done against a restoring force, so we know the work done has to be equal to half kx square. Again, we have derived this in our chapter Work, Energy, Power, work done by a restoring force. If you were doing work against a gravitational force, then it would have been mgh, but against a restoring force, work done will be potential energy, that is half kx square. Similarly, the kinetic energy we know for an oscillator is the same, half mv square. So you may write this total energy as the sum of kinetic energy plus half kx square, which is the potential energy. Now here, if I substitute for kinetic energy, this is last session we have derived for velocity of an oscillator, last session I have derived the formula for you, minus A omega sine omega t plus phi, where A is the amplitude, omega is the angular frequency, and this is the phase of that oscillation. So we may write this as half m v square would be a square omega square sine square omega t plus phi. Also we know x, again from the previous session, x is a cos omega t plus phi, the displacement of any simple harmonic oscillator. So the potential energy can be written as half k a square cos square omega t plus phi. Now we know that this m omega square is k square. So you may take half k a square outside, because m omega square is k and then we have an a square here. From here also I have taken half k a square outside, and inside the bracket we have sine square omega t plus phi plus cos square omega t plus phi, which you know is 1. So we know that the total energy of this simple harmonic oscillator is half ka square, showing you that the simple harmonic oscillator has a total energy which is a constant, because k, as you know, is a constant depending on the frequency and the mass of the oscillator, and because we know k is equal to m omega square. So it depends on the mass and the angular frequency, which is a constant, and amplitude is the maximum displacement of the particle from the mean position, again a constant. So we see that the total energy of the oscillator is a constant, where we have this oscillator at the mean position, and these are the extreme positions. So plus A and minus A. If you go back to your previous session, you will see at the extreme positions where the oscillator is returning back, the velocity is 0 at both positions. But here you have the velocity which is maximum. So the kinetic energy at the extreme positions is 0, but at the mean position it will be maximum. Potential energy is half kx square. So it's proportional to x. So greater the displacement, maximum displacement would mean the potential energy is maximum at the two extremes, and at the mean position the potential energy will be 0, because half kx square, x is 0. So what I'm trying to tell you is at the extreme positions, all of the kinetic energy has been converted to potential energy. At the mean position, all of the potential energy has been converted to kinetic energy, but the total mechanical energy, total energy will remain a constant throughout the oscillation. We need to represent the variation of this energy with respect to time first, and then with respect to displacement. So what we're going to do is, first we're going to use the formula, the kinetic energy being equal to half k a square sine square omega t plus phi, after substituting for V. And potential energy we know is half k a square cos square omega t plus phi, because you substitute for x. So if you're going to show the variation of energy with time, we have here the energy. Okay, so half k square is a constant. This kinetic energy is going to vary as the sine square. Sine square would mean it doesn't take any negative values. So at an angle which is 0, that is time t equal to 0, sine square 0. When this time is 0, you will have sine square 0 would be 0 minimum. Then at time t by 4, which is, I'm taking the simplest equation where phi, the phase constant, is 0. So let's write this as omega t. Phase constant 0 would be omega t. So when time t by 4, omega t you know will be pi by 2. So sin pi by 2 is 90, sin 90 is maximum. So you have maximum value which is corresponding to half k a square, which is the total value. Then when t by 2 you know it will be pi, angle is pi. So sin 180 will be 0 again. Then at 3t by 4 you know that is going to be 3 pi by 2, which is 270, but square, and it will become plus 1. And at to complete one time period, you will have 0 again. So a sine curve like this will represent the kinetic energy here. If you take the potential energy, is the square of cosine function. So at time t equal to 0, cos 0 is 1, so it's already at the maximum. Then by the time you come to t by 4, cos 90 is 0. Pi cos pi is minus 1, but square it and you have maximum here. Then 0 and maximum. So this dotted line, this dotted curve will give you the potential energy curve. So this is variation of kinetic energy and potential energy with respect to time. You can also show this variation of, and the total energy will always remain a constant at half Ka square. You can also show the variation of potential energy and kinetic energy with respect to displacement. In which case, we have this axis representing the displacement and this axis here showing you the energy. So this is x equal to 0. Here we have maximum displacement plus a, and here we have minus a, the maximum to the other side. So here we will use the formula. You know, at the extreme position, kinetic energy is half mv square, and at the extreme positions the velocity is 0 because the body is returning back. So velocity is 0. So kinetic energy is 0 at the extreme positions here. But at the mean position, the velocity is maximum. So we go on to give maximum value here, and this will be your kinetic energy curve. Whereas your potential energy, you will be using the formula half kx square. So at the two extremes, where x is maximum, you have maximum potential energy. That is here and here. But at the mean position, when x is 0, you will have the minimum 0 potential energy. So we will represent it using the dotted curve here. But the total energy will be half Ka square. So as the particle oscillates to the right and to the left extreme, you will see that kinetic energy gets converted to potential energy and so on. But the total energy will remain a constant. So these are the two graphs that you have. One showing the variation of energy with respect to time, and also showing the variation with respect to displacement. We now go on to discuss another example of a simple harmonic oscillator. We did one already, which is the linear oscillator like the block and the spring system. We also found an expression for its time period. We now go on to discuss the simple pendulum, which is also a simple harmonic oscillator. We are going to show that. So for a simple pendulum, we have, you are all familiar with this simple pendulum. We have a fixed support from which, let's say we have a string of length L and a bob here, a metal bob of mass M. Now I pull it slightly to the right, displace it through, let's say, an angle theta, and I'm going to leave it so that it's now going to go to and exhibit to and fro motion about this mean position. Now if I look at the forces acting on the bob at this position, we have the weight of the bob acting in the downward direction, mg. We have the tension T, which is acting towards the point of support, and this angle being theta, because they are corresponding angles. You may take this as the cosine, the adjacent side. So this, if I resolve mg, this component will be mg cos theta, and we'll have another component here which is mg sin theta. So the two components mg, this component has a adjacent component mg cos theta and the opposite component, that is mg sin theta. Now from here it is clear that this mg cos theta is actually balancing the tension, whereas mg sin theta is the restoring force that is going to bring it back to the mean position. So the restoring force here is minus mg sin theta, restoring force, because it is going to, as theta increases, it's going to act in the opposite direction to decrease theta. Now the torque acting on this will be, we know R cross F, which is, the R is the distance from the point, from the axis of rotation. So that distance will be the L, length of the string. So we may write L, the restoring force is mg sin theta with a negative sign. That is the torque. This restoring torque, we give it a negative sign, I told you, because it tries to bring it back to the equilibrium position. Now for small angles, if you have displaced it through very small angles, and if you take theta in radians, you may approximate sin theta to be, sin theta can be approximated to be almost equal to theta if you are measuring theta in radian, the SI unit. So we may write tau is equal to minus mgl into theta. But we also know from last year, from rotational motion, this restoring torque can be expressed as I into alpha, where we have the analogous equation F equal to ma, where mass is replaced with moment of inertia and acceleration, linear acceleration is replaced with angular acceleration, and the force is replaced with torque in rotational motion. So we have this formula tau equal to I alpha. Now I may equate the right hand sides and write I alpha is therefore equal to minus mgl into theta, or I may write this as alpha is equal to minus mgl by I into theta. Now if you look at this, this is very similar to the equation we got for a simple harmonic oscillator, where acceleration is minus omega square x. Here linear acceleration is replaced with angular acceleration. X, the linear displacement, is replaced with the angular displacement, which means that this omega square is this constant mgl by I, where m is the mass of the ball, g is acceleration due to gravity, l is the length of the pendulum, and I is the moment of inertia. So you may compare this and say, you may write that this omega is therefore equal to root of mgl by I, which is the moment of inertia, which you know is mr square, r being the distance from the axis of rotation, which is L here. So I may write this as ml square for moment of inertia, mr square. So I can cancel this and I will see that omega is equal to root of g by L, from which I can go on to get an expression for the time period of the simple pendulum as time period we know is equal to 2 pi by omega, or this is going to be 2 pi root of, omega is in the denominator, so this is going to be L by G. Now this equation very clearly tells us that the time period of the simple pendulum is independent of the mass of the ball, it depends only on the length of the string. Okay, so it is independent of mass of ball, depends only on the length of the string. So we have shown from this equation being similar to A equal to minus omega square x that this simple pendulum executes simple harmonic motion. We have also found out a time period, an expression for the time period. After this, the last part of the chapter, we need to discuss what we call as free oscillations and the damped oscillations, also forced oscillations. Now, if you have, let's for example take a simple pendulum. We have been talking about the amplitude being a constant. When I said energy, total energy of a simple harmonic oscillator, half Ka square, I said amplitude is a constant. Now this happens in ideal conditions. For example, suppose we have a simple pendulum. As it oscillates, there will always be an air drag, a dragging force, air friction. There will also be friction at the point of support. Because of this, what will happen is the amplitude will continuously decrease with time, and such oscillations are what you call as damped oscillations. If you put the same thing, simple pendulum, into water, you will see that the drag because of the viscous force of water is greater, and the oscillations will be damped faster. Similarly, if you're sitting on a swing and slowly, if you don't give yourself an external push, the oscillations will die down finally, and such oscillations are what you call as damped oscillation. Damped oscillations. Now, if you, let's say for a swing or a simple pendulum, you slightly disturb it and let it oscillate freely, the frequency with which it will oscillate freely without the application of an external force is what you call as the free oscillation, and the frequency of that oscillation is what you call as the natural frequency of the oscillator, omega. Without any external force driving it, the natural frequency with which it is oscillating, the free oscillation, that is denoted by omega. Now, if you're sitting on a swing, you can do one thing. You can actually, as you come back, every time you come back to the starting point, you can kick the ground with your foot, thereby giving yourself an external push. So this external force is now driving your oscillation, and such oscillations which are driven by an external force is what you call as forced oscillation or driven oscillation. So the force is also being applied periodically, meaning every time you come back, you're kicking the ground with your foot. So there is a force which is applied periodically. So the frequency of the driving force is what you will denote as omega d. So you see, every oscillator which is under forced oscillations, that is on which an external force is acting, has two frequencies. One, its natural frequency omega, which is the frequency of the free oscillations when no external force is applied. It has also got the driving force frequency, meaning this is the frequency of the driving force. The external force that is being applied periodically has its own frequency, that is the driving frequency. Now, if the natural frequency of the oscillator becomes equal to the frequency of the driving force, then what happens is the oscillator will now swing with maximum amplitude, and that phenomenon is what you call as resonance. You would have noticed that while you're swinging, if the frequency with which you're kicking the ground becomes equal to the natural frequency of the swing, then you know you can swing with maximum amplitude, and that is what you call as the phenomenon of resonance. So resonance is when the natural frequency of the oscillator becomes equal to the frequency of the driving force, and the oscillator now oscillates with maximum amplitude. So that is why, see, all buildings and mechanical structures have their own natural frequency. So if an external force, a very large external force, whose frequency matches the natural frequency of the structure, is applied on the structure, then you will see that the structure will collapse. And that is what happens in an earthquake. You will see some buildings remain intact, whereas other buildings completely collapse. This is because the natural frequency of the building must match the frequency of the earthquake, in which case that building will oscillate with maximum amplitude and it will collapse. Other buildings can remain intact. Also, aircraft engineers have to be very careful to design the aircraft in such a manner that the vibration, the oscillations of the wing, the frequency of the oscillations of the wing do not match the frequency of the engine, because if it does, then you know resonance will take place and how disastrous it can be. So we've come to the end of our chapter oscillations. Today we started our discussion with force laws for simple harmonic oscillator. We went on to derive an expression for the kinetic energy, the potential energy and the total energy of a simple harmonic oscillator. We also drew graphs to show the variation of the energy with time and displacement. We discussed two examples of simple harmonic oscillators. One, the block and spring system, also the simple pendulum. And last we discussed damped oscillations, free oscillations, and driven or forced oscillations, and also the phenomenon of resonance. Thank you and good night.